Well, thanks so much for having me. I'm very happy to be here, and thanks for the organizers. It was a lovely conference, and I'm excited for the workshop to come. So today I'm going to talk a little bit in more depth about how about the physics behind TDEs specifically. Eric gave a great overview of black holes, and also about how these disruptions actually produce the light that we observe, and then how we can look at these observations and compare them with our models. And so we must have, Kate and I were on the same page in our background. So my first set of slides is kind of similar to Kate's, but goes into a little bit more depth, I think. So zooming out from the black hole to the stars that will eventually become the tidal disrupted stars that we see. If we go through our own galaxy, as Kate pointed out, there are tons and tons and tons of stars. And so even though the black hole is this extreme massive force at the center of the galaxy, its mass is of our own galaxy is 4 million solar masses, but black holes can be millions to billions of solar masses. The actual mass of the stars in the galaxy at large is orders of magnitude larger. And so actually for most of the stars in the galaxy, they're just kind of hanging out and they don't know that they have this massive black hole at the center, which for those of us trying to study the black holes makes it actually difficult to learn about them. And so I guess I won't play that again, but what you could see there, actually I think I can pull up just the end bit there. Nope, that's fine. What you could see there at the end was the motions of the stars very, very close to the black hole. Tried to redo it there. Yeah, the motions of the stars very, very close to the black hole that were measured, as Kate said, by the Galactic Center Group. And so in our own galaxy, as Kate said, we actually are able to look super, super close, measure those orbits, and constrain the black hole mass that way. But if we look at other galaxies, those central stars are obscured by all of the other stars in the way. And we just can't get the precise enough measurements to constrain those orbits on those small size scales like this. And so we need the black hole to do something dramatic to create a bunch of gas to show us that it's there, and also to let us measure its properties. And so some of the questions, very general questions that honestly drive a lot of our research are, what are the masses of the black holes at the centers of galaxies, and also how did they get to be so big? Because black holes, we see black holes born from stellar explosions, but then they're about the mass of the stars that explode. And the mass of the black holes in the centers of galaxies are orders of magnitude larger, so large that it's actually difficult to explain them by simply having the stellar mass black holes accrete gas from their surroundings over the age of the universe. So again, a lot of this has already been mentioned, but how do black holes grow? Well, actually, one of the important ways they grow that hasn't been discussed, but is measured with gravitational wave observatories, is by merging and colliding with other black holes. And so small stellar mass black holes can do this. If there's stars that were in a binary and then eventually black holes form from those stars in a binary, those can merge. But also we have large-scale galaxy mergers. Our own galaxy will eventually merge with Andromeda, and the black holes at the center will eventually go to the center and merge. So that's one way they can grow. But they can also, you need black holes to start with there. You can also pull in surrounding mass through mass accretion. And so one thing that I find really helpful for understanding accretion better, because I don't think it's super obvious, and I'm glad that Eric gave a bit of an overview, is to think of it by looking at wishing well analogies. And so there's a coin in a wishing well where the coin eventually falls in, and it's the friction of the coin that's causing it to lose energy and fall in. Otherwise, it would just keep orbiting the wishing well. But if we look at marbles instead, and you guys have maybe already seen these sorts of videos, you have friction between the marble and the wishing well surface, but you also have interactions between the marbles. And so that's actually more analogous to what's happening in accretion. Like Eric said, we have these viscous drag forces, but it's pretty analogous to the sort of friction forces that you see between the marbles. And I think that's really well illustrated by this other video that looks like a simulation that is just glow-in-the-dark marbles in a wishing well. If someone just kind of showed me a snapshot of this, I'd be like, oh yeah, that could be like a SPH simulation of just like gas particles. Seems reasonable. And in fact, if you look at a video of a simulation, it conveniently, I didn't do this, conveniently colors are similar. And this is actually one of the conference participants' early work. This is an actual accretion simulation. Looks pretty similar. So it works out as a very nice analogy, I think anyway. So this is how accretion works. This is how the mass eventually falls into the black hole. But how does the gas get there? So we like, in this conference and workshop, to throw stars at black holes and see what happens. And so a tidal disruption event is when the star is ripped apart by the tidal gravity of the black hole. And I'm going to show another simulation. You might not be able to see the little dots that are the black hole and the star, but once the simulation starts, it will be more obvious. So a star comes in, and it's ripped apart. And then in the most extreme case, it's completely ripped apart. And about half the mass is going to be bound to the black hole and eventually accrete. And that accretion after the actual disruption is what produces the flare we observe. Half of the mass is going to leave unbound from the system. And one thing to note here, I'm going to show this video again, but this time I've overplotted the approximate orbit. The star isn't plunging directly into the black hole. I mean, that could happen, but then we wouldn't actually be able to see anything because all of the mass would be inside the event horizon. So when things get exciting is when the black hole just passes very, very near the black hole in this very, very eccentric orbit. So it's not at all like the sort of Keplerian orbit, or well, it is approximately a Keplerian orbit. It's not at all like the circular, more circular orbits we see in a lot of the planets in our solar system. In this case, the pericenter is tiny compared to the apocenter, and I'll go into more detail about that on following slides. But first, I think it's helpful to just do a tiny bit of background on tidal gravity. Eric mentioned this, but obviously a really easy analogy is just the tides on Earth. This is not to scale, but on Earth, both the moon and the sun pull on the Earth. And the tidal gravity is just the difference in that force, and we get it because the gravitational force is dependent on the radius from the perturbing object. So if we just focus on the moon for now, the tidal force, you can write down pretty easily as just the difference in the gravitational force from one side of the Earth onto the other side of the Earth. The way I like to think about it is that one part of the ocean is getting pulled ahead, the other part's getting left behind. If you plug in values for the gravitational force, where the big R is just the separation between the center of masses, and then the offset is the size of the body that's getting in this tidally perturbed, you can really quickly estimate the size of the tidal force. You do a couple Taylor expansions, and this comes out without any calculus or anything. But what's important here, this is for our Earth-Moon system, but this is a general equation for tides, right? It's basically the force of gravity of the perturbing object times the size of the object getting perturbed over its separation. And now, I noted this wasn't to scale earlier, the change in the height of the ocean from tides is about a millionth the size of the Earth, and so if it were actually to scale, you just wouldn't see anything. But if you had a much stronger gravitational force, if we have an interstellar situation, we put a black hole there, then we get the dramatic tidal wave tides that you see in interstellar. You also would eventually, if you're close enough, stretch out the Earth and rip it apart. This is not a simulation, but I am going to show some simulations of stars getting disrupted, and importantly, people actually do care about planet disruption as well. It's an interesting topic, but we're mostly going to focus on stars because they have more mass that they can feed the black hole with. And so this is another simulation of a tidal disruption, but now we're in the perspective of the star, and so you can really see those tidal warps happen. And so the star is getting pulled in different directions. It's rotating partly because it's on an orbit around the black hole and partly because the star is getting spun up a bit by the black hole. Eventually, it's just fully ripped apart. And so if we think about the geometry of the orbit here, we have a star that comes in. It's disrupted near pericenter where the tidal gravity is the strongest. Part of it will be bound to the black hole. Part of it will be heading off into space. But something that I mentioned early and I think is important to talk about now is most of these orbits are we'll get back to that picture, most of these orbits are very, very eccentric. And the simple reason to understand this is that the picture I showed earlier of the galaxy showed that there were a ton of stars, but the majority of those stars are at larger radii. Even if you have a relatively steep density profile, you need a density profile steeper than r to the minus 3 to start putting more stars close to the black hole. So even with a steep density profile, most of the stars are going to be at larger radii. And so most of the stars that are going to be disrupted, if they're going to be disrupted, need to be on almost radial, deeply plunging orbits with very, very high eccentricities. And so if you look at the orbital parameters here, we have the pericenter radius, the semi-major axis, and the apocenter radius, where the pericenter is where it's getting disrupted, and the apocenter for this might be of order a parsec away. It's like the sphere of influence of the black hole. And the eccentricities in these systems, for most of the TDEs that we observe, we think are above 0.99 or so. And so basically, the pericenter is tiny compared to the orbit of the star. And what that means energetically, actually, is that the star is very, very weakly bound to the black hole when it is disrupted. And that's why in a full disruption here, where the star is completely disrupted, we actually only expect about half of the mass of the star to return and the other half to head out into space. Because if you think of the center of mass of the star as just barely bound to the black hole, when you no longer have the gravity of the star keeping it together, half of it just leaves unbound. And so we can estimate the radius where this tidal force overwhelms the self-gravity of the star by equating these two terms. And so if we have a system here, this would be, I wrote tidal radius, but this, we can just think of this as the pericenter radius of the orbit, and then the value of that pericenter that will produce this disruption. And so we already calculated tidal forces, right? So in this case, for the black hole star system, it's the gravity of the black hole times the ratio of the star's radius to the tidal radius. The self-binding energy of the star is essentially its gravitational force with its mass squared, because it's the mass of the star binding itself. And you can set these two equal to each other. Also, I'm definitely ignoring like terms of 2 and such, like Eric said. You can set them equal to each other, and you can solve for the tidal radius, and you get this really simple equation that's just dependent on the properties of the star, its mass and radius, and also the black hole mass. And so if you have a much more extended star with very loosely bound envelope, like a red giant star, for example, it can get disrupted at larger radii. But if you have a very, very compact star, like if people have heard of like white dwarfs and neutron stars and things like that, that are much denser, more close in density to a black hole, but still less dense than that, then they need to be disrupted. They won't get disrupted until they're much closer to the black hole. And so I'm going to show this hydro simulation that I was showing again, but this time I've overplotted multiple orbits. And so the largest orbit is probably closer to the initial orbit of the star, but then the smaller orbits, you'll see that some of the mass after disruption returns more quickly, and some of it takes longer to return. And so there's this spread in orbits of the gas after disruption, and what this means is that all of the mass doesn't fall back to the black hole at once. It actually takes time for the least bound material. It takes longer for the least bound material to return, and so we can calculate the spread in these orbital timescales to determine how quickly the mass returns to the black hole. And we call this the mass fallback rate. And this is really important because if we think that mass is powering the flares of light that we see, then we can potentially connect this mass return rate to the luminosity that we actually see. And so I like to break up, so this mass fallback rate is dmdt, that's what I'll use for the rest of the talk, or m dot, but I tried to take those out, so it's probably mostly dmdt, which is the rate of mass return to pericenter. And you can break this up into mass energy distribution and the relationship between orbital energy and orbital time scale. And so don't worry about the fact that, we'll derive this analytically, but then this mass energy distribution is the initial distribution of orbital energy in the star, convolved a little bit with how the actual hydrodynamics of disruption changes that spread in orbital energy in the star. And then this relation here, we can actually just calculate from Kepler's laws. So I'm going to quickly do that. And that will hopefully help us better understand the spread in orbital energy that we get after disruption. And so like I was saying, at larger radius, there's less bound material. And if you write down the equation for orbital energy, you have this proportionality where things that are, important note is this is negative, right? So if you're closer to the black hole, you're more bound. So you have a higher magnitude of energy, but it's more negative. So out here, you're closer to what we call a zero energy orbit that's basically unbound. In here, you're very, very tightly bound, and your semi-major axis is smaller. If we also write down the formula for orbital period, again, just from Kepler's laws, you see that the orbital period is proportional, increases with semi-major axis. And so stuff out here is going to take longer to orbit. We can combine those two into a relation for the orbital timescale as a function of orbital energy. And from that, we can actually calculate this relationship between orbital energy and time, because it's going to be the same dependence as it is on orbital period. So we basically flip this relation around, get orbital energy in terms of period, and take the derivative. And it's a power law, it's a pretty easy derivative to take. You get this t to the minus 5/3 relation. And so what we would expect from this disruption is if the mass energy distribution in the debris doesn't change that much, the mass fallback rate should follow a t to the minus 5/3 power law. And it turns out that the material that comes back at earliest times does have varying mass energy distribution, but the material that comes back at later times that's closer to the core of the star, that was less bound to the black hole to start with, has a much flatter distribution of mass and orbital energy. So once you get towards the core of the star, this becomes relatively constant. And so if you actually do simulations of this disruption process, we find that we sort of plateau at, well, this isn't a plateau. You converge at late times to t to the minus 5/3 power law. And just to note, this is a snapshot of a disrupted star, and as you go from this outer edge inward, you go from material that's more bound to the black hole to a material that was more bound to the star and less bound to the black hole, and this correlates with mass return time scale. So on average, we would expect the mass that returns at early times to be coming from the outer layers of our stars, and the mass that returns at much later times to be coming from closer to the core of the stars, which turns out to be interesting for composition predictions in the mass, but I probably won't have time to get to that today. You can ask me. Another dependence that you can calculate analytically, but it takes a bit longer, and so I didn't do it here, is the mass fallback timescale is dependent on black hole mass. And so this is this mass fallback timescale I showed before. The shape looks different because the last plot was in log-log space, if you didn't notice, and this one has linear time. And so you can see a more power law looking, I guess, decline here. But notably, if you change the mass of the disrupting black hole, you go from really short fallback rates to much longer fallback rates. So this is, I think, a 10 to the 5 stellar mass black hole, so it's like 10 times smaller than our central black hole. This is 10 to the 8, so it's 1,000 times or 100 times bigger. And so there's a scale of 1,000 difference, and it really makes a dramatic effect on the mass fallback rate. And the way that I like to think about that is basically the black hole mass is a constant in the equation in the mass fallback time scale. And so if you're increasing the mass, it's just spreading the debris further apart in time. It's increasing the energy of all of them, but it's spreading it in time. And so you get material returning at later times across the board. Oh, yeah, and this dependence goes as t to the 1/2, the black hole mass to the 1/2 power. And so you go from timescales of like weeks to years. So these are all observable in what we call transients, so they're changing on human timescales, but there's observable difference between the two if we can connect the light curves to the mass fallback rates. But how is this mass actually converted into energy? So we started talking a bit about accretion. Other people have already talked about this as well. But I think both Eric and Kate mentioned that these debris streams are not initially going to be in these nice accretion disks. Initially, the debris streams, like the initial stellar orbits, are going to be pretty eccentric. They're going to be less eccentric than the star was, but they're still not in a nice circular orbit around the black hole, accreting kind of like the donut that we see in the Event Horizon Telescope. And Eric mentioned this, but one of the ways that we can actually start to change the orbits is by this apsidal precession due to general relativity. And so most of the previous stuff I was talking about was just Keplerian orbits, but actually, if the orbital pericenter is getting within a factor of 10 or so, or even 100 of the gravitational radius of the black hole of the event horizon, you need to use general relativity to think about how that orbit is changing with time. And one of the main differences is it just changes the orientation of the pericenter. And so you'd get, if I'd shown multiple orbits, it would look like this. But in the case of a tidal disruption event, if you actually have mass streaming along this, if it just collides once, it's going to disrupt the incoming stream. And so there's been a lot of work done in our field to try to model this stream collision process. I'm showing a snapshot of one of these simulations. This is, the color corresponds to the density of the gas. So the yellow is denser and the black is less dense. And you can see the initial setup of the simulation has gas on these streamlines. And so they're modeling the incoming gas and seeing what happens when it collides using parameters that are reasonable for these disruptions. And one thing that they immediately find is it is very efficient at dissipating energy. You both get large outflows, but you also get mass that's able to fall back to the black hole and accumulate. And I'll show a simulation of that in a little bit. You can potentially get shocks elsewhere in the orbit. One interesting tidal effect is that you also will get these nozzle shocks at pericenter, where basically adjacent ballistic orbits are nearly intersecting at pericenter. And so even though the majority of the energy is along the direction of the orbital velocity, there's also this collapse effect. And so that vertical component can also produce a shock and potentially help release some of the energy. And so that's this snapshot of a simulation. The red is the denser. You can see it's initially on this orbit, but then some of this gas is starting to look more circular and more disk-like. So there's a lot of debate in the field right now and in this past conference about how this happens. But if gas is able to lose energy and transport some of its angular momentum out, you'll eventually form a disk. And so this disk will, as Eric said, be incredibly efficient at radiating energy, and it should be very, very bright. And so I think this is a good point to kind of transition towards what we actually theoretically expected to observe from these tidal disruptions. So this was an interesting event in that, or an interesting type of astronomical observation in that it was predicted long before, or the actual luminosity, the way that the light curve was expected to look was predicted long before the actual observations were made. And in some ways, they were consistent. So one of the things, for the rest of this talk, if I mention luminosities, that's just the power, so it's the energy per time, the way that we talk about it as astronomers. But we very broadly expected to see a light curve that somewhat followed this mass fallback rate to the black hole times some efficiency, which again, as Eric said, can get very, very high, times the speed of light squared, so an MC squared relationship. And again, like I talked about, we expected this luminosity to follow this T to the minus 5/3 power law because the mass fallback rate does. And actually, some of the first events, if you just look at the total luminosity, do seem to have a peak and then a T to the minus 5/3 decline that is relatively consistent with that particular prediction. But there are also a lot of surprises, which always comes in when you try to compare your theory with real life. So one notable one is that we really expected to observe these events as X-ray bright events. Most of the accretion disks around black holes had previously been observed from the sort of active galactic nuclei situations that Kate talked about and others have a lot of X-rays. But these events actually were quite bright in optical and UV. And so I'm plotting here the light curves in different bands. So if this is the total emitted energy or our estimate of it, what we actually see with telescopes are these points in different, broken up in the electromagnetic spectrum. And the points down here are mostly UV wavelengths. The points up here are mostly optical wavelengths. The very nice offset is just done by hand to be able to see all of the light curves. So it's not actually that these optical bands are significantly brighter. It's just that we can look at this plot and not just see a jumble of lines. Yeah, but there wasn't, for many of these events, there's very little X-ray emission. So there are events that are X-ray bright, but in the majority of these events actually show no X-ray emission at all, and significant optical and UV emission. And so to better understand why this was confusing to us, you can actually turn to another pretty simple physics principle, which is Planck's law, or Planck's law. So the black body emission here, so I'll go briefly through why this tells us that why this led us to believe that we were expecting X-ray emission. So for black body emission, we're assuming that all of the photons are trapped long enough to share their energy and then are emitted at some surface. And so to try to kind of like, I guess in this aspect of modeling, I think we generally do a sort of spherical cow physics approximation. And so we're assuming instead of a disk that we have a sphere here. And so there's a sphere of order the size of the disk. The gas we know is quite dense, so it makes sense to think of it as optically thick. It makes sense to think of the photons as trapped. And the photons are going to be reflecting and absorbing and re-emitting and sharing their energy. And then when they eventually diffuse out, what we'd expect to see in this black body emission case is a thermal spectrum that's peaked around a characteristic wavelength. So this is a plot of a thermal spectrum in luminosity versus wavelength, where there's a variety of wavelengths that are emitting, but it's really strongly peaked around this characteristic wavelength. And so black body emission is pretty simple to explain theoretically, or it's pretty simple to write down the equations for theoretically. The luminosity is just dependent on the temperature and the radius, or equivalently, the temperature is dependent on the luminosity and the radius. And so for a constant luminosity, the smaller emitter is hotter, and that's kind of what I'm showing here, or trying to show with the blue, more UV-like bands here. And that's just because there's more energy per photon. And so if we actually plug in some numbers, we can understand why we were expecting so much X-ray emission from these disks. If we start with a reasonable luminosity, this is close to the maximum accreting luminosity of a black hole, like the one in our own galaxy. And then we put in a disk radius, and I didn't go through the math for this, but the approximate size of a disk you would expect to form is pretty close to the size of the tidal radius of the pericenter. And if you plug in the numbers, what you find is that the disk temperature should be very, very hot, a few times 10 to the 5 Kelvin at minimum. And if I didn't just do this in the spherical cow approximation and I actually modeled a disk, I would get even more emission at smaller wavelengths because you see down to those smaller wavelengths as well. And so if I plot that distribution of luminosity as a function of wavelength here, so this is, you can just think of this as the luminosity at each wavelength, and this is the wavelength. You don't really have to read the numbers on this plot, but you can just see here the peak is going to be in the UV or in the X-rays at these temperatures for the disks that we were expecting to form. Instead, what we actually saw for a lot of these events were temperatures that were an order of magnitude lower. And so this is actual data. I'm showing the same parameters on the axes, but now the points of the data, the line is the model fit. Now we're peaking in the UV with a lot of emission in the optical. And so if we put those side by side, it's a bit easier to see. The peak of our expectation is completely off the plot here. So we're not seeing any X-rays in that event, and we're seeing a ton of optical emission. And this is really confusing when you think about the size scale of the disk that we think is emitting most of the energy. And so if we plug in these new numbers, what we find is an emitting surface that's about 100 times larger than the disk. So this is approximately what that would look like. And that is unlike what we see in a lot of other disk emission from compact objects. But for TDEs, it's actually not incredibly surprising when well, at least we saw this and we're like, oh yes, now we can explain this in this other way. And the reason for that is that the stream collisions that actually circularize the material into a disk also produce a lot of mass and outflows. So some of the gas will make it down to the black hole, but a lot of other gas will be thrown out. And then also, once you eventually form a disk, when you're accreting at the very, very high mass fallback rates that we went through earlier, you're very close to this maximum accretion limit, maximum accretion luminosity limit for any accreting object, which is the point where the radiation pressure actually matches the force of gravity inwards, or the gravitational pressure inwards. And so once you get to that limit, it's very hard to continue to bring the gas in that will then produce the luminosity. And so, and I guess, and the point there is that you can also produce winds at that point. And so both the process of circularizing debris through stream collisions and also the eventual very strong winds that can be launched from these black holes that are accreting near their maximum limit can produce outflows around the black hole. And so if we look at that, this snapshot that I've been showing is another stream collision simulation. It doesn't have the initial debris stream on it because this simulation starts at the point of the intersecting streams, but it would look something like this. I'm just going to play it because simulations are nice to look at. And so you can see the stream collisions very quickly are throwing mass out at larger radii, even as they're also helping a disk form. And if we look at the different components here, we have the precessing debris stream, we have an outflowing wind, and then if we look with our telescopes, at some point in this gas, we'll become optically thick. And so we won't actually be looking down to the scales of the accretion disk and generally of the stream collisions either. Instead, we'll be looking at this thermal emission at larger radii, this black body photosphere that's evolving. I guess I mentioned this earlier, but accretion disks can also produce similar outflows. This is a sort of artist illustration of what these disks might look like, where you have a black hole at the center. You have, in this case, a puffy disk because you're pushing, the radiation pressure is pushing gas out, and at some point it's pushing it into winds that are at larger radii. But actually, if you look at a simulation of one of these events, all of this behavior is happening on tiny size scales. So this is, I think this is tracing, the lines here are tracing luminosity out. So there's more luminosity in jets in this simulation, which I won't talk about, but Odell will talk about. But if you actually estimate the photosphere, where things become optically thick, where the thermal emission would be coming from, you get this very, very large radii in yellow here that's of orders of magnitude larger than the disk that's forming in the center in that simulation. And so this is really annoying for trying to study the disks, and it's possible at late times we're actually starting to see some of these disks better. But for this initial flare, what it can do is slightly simplify the modeling of these events. And the reason for this is because we can just model a power source in an evolving photosphere instead of the intricate disk evolution that we would need to do if we were actually getting X-ray spectrum. So there's a few events that we have X-ray spectrum from, and we can model that evolution, and that's very nice for comparison. But for the majority of them, what we're doing is modeling some sort of power source with an evolving photosphere. And there's different ways of doing this depending on your preferred theory, but it's generally some combination of this. And if we do that, so this plot I was showing earlier, the lines that you see, so the points are data, but the lines that you see are from a model like this that I developed with collaborators. And so one of the really nice things about that is that we can use this model to connect the mass fallback rate that I talked about earlier that are connected to the black hole mass with the actual luminosity that we see. And what we're starting to see in observations is it seems like like predicted from mass 12 vector rates, the longer-lived flares seem to mostly be coming from larger black hole masses. This is actually data from 2 different events. I've removed the axes here because I think it's mostly just the black hole mass here is mostly constraining the or changing the time scale in these events. And so the longer-lived event has a black hole mass of around 10 million solar masses, which you can confirm with other estimates of black hole mass, and the smaller one has a black hole mass that's about 10 times smaller. And so this is one of the ways that we're trying to use modeling to actually constrain the properties of the system. And then in this few number of cases where we actually have, for example, X-ray data, we can then also model the accretion disk and see what sort of black hole masses we get from that and see if it's consistent, which is really nice. I think I went pretty fast, but I actually am close to my recap here, I guess because some of the stuff was already talked about. But basically, recap, when stars get too close to a black hole, they're ripped apart by the tidal gravity. This fuels accretion, which has been discussed by a few different people, but I think is really nicely thought about just as the sort of effective friction between the gas that's infalling to the black hole. And as other people have already said, black holes are very messy eaters, and so we can discover black holes when they are accreting. And finally, we're starting to be able to measure some of these properties of the black holes. One of the ways that we're doing that right now is comparing the time scales of the light curves that we get to the expected black hole masses.
All right, thanks so much, Brenna. So now we've had a little bit more detail about tidal disruption events in particular for black holes, and we have plenty of time for questions. So people will be going around with microphones to hand you the microphone to speak into for your question.
Okay. Maybe I misheard this, but I just wanted to get a clarification on it. You said that neutron stars won't get disrupted till they're closer to like that perihelion point, versus like a red giant would get disrupted like sooner.
Yeah.
Is that due to like their eccentricities, their mass, their radii? Like what would cause that to happen?
I guess I went too fast through this beginning part. Let's find the equation here. So basically that's coming from this tidal radius equation. It's because the binding energy of these denser objects is so much higher. And so the tidal gravity that's needed to rip them apart needs to be higher as well. And so it comes straight from this, RT is equal to R star MH over M star. If you plug in the much smaller, so a neutron star has similar mass of order the sun, but radius is like, I think to the size of New York City or something like that. So the radius is way, way, way smaller. And that's just what's driving it. But it is just a binding energy argument. It's not quite as bound as a black hole, but it's getting close.
Yeah, we'll go over here.
Does the star, as it's approaching the black hole, does it turn off? Because probably its innards have been pulled apart, and then would you see a star go out?
Yeah, that's an interesting question. So basically, does the nuclear burning change when you get close to the black hole? If you fully rip apart the star, then yeah, the nuclear burning is ongoing because it's balancing the force of gravity in the star, and you've removed that self-binding force of gravity, and so you're no longer going to have nuclear burning. If a star passes through and doesn't get fully disrupted, and you just kind of rip off the outer layers, it will potentially continue to live slightly different, but compared to a star that's fully ripped apart, much more normal life. And those are stars that we actually are trying to look for and think about how they might be slightly different. They will still be nuclear burning, but if you like rip off the outer layers of the star, you kind of put it on a slightly different lifetime sequence than how it was born. And so it will potentially live longer, for example, because it won't be burning quite as intensely as a more massive star is.
The graphs that you had, the brightness versus time, the time scale was in days. Mm-hmm. So I'm not sure if I'm asking the right question, but it made me think that if a tidal event is detected, you can actually measure a mass change in a time frame like days?
Yeah. So that's generally, when I think of what we term like transient astronomy, that's things that do change on timescales of less than years or so. And so in this case, you are changing the luminosity by the other plot just had brightness. This one actually has the luminosity, which I don't know if you can see, but is changing by orders of magnitude on like month timescales. And so that's actually how we see these, how the observers will probably talk about this more later, but how they find these events is by difference imaging in the galaxy, where they looked at a part of the galaxy and there wasn't anything there, and they look back a few days later and suddenly there's a bright source. And that is days time scale.
Have they ever seen a TDE around a binary black hole system?
Oh, I'm very interested in this topic right now, theoretically. So we don't know, I guess is the short answer. Depending on how close the binary black hole is, it may or may not dramatically change the light curve. So if you're at very large radii, there could be a second binary, and it's not even changing the orbital dynamics of the stars, let alone the eventual flare that you would see if it's disrupted. If the binary comes a little bit closer in, you start having these interesting three-body dynamics. So the three-body problem has gotten a lot of, sci-fi novel has gotten a lot of interest recently. But basically, you can have crazy orbital changes over short time scales if you have three-body dynamics. In the case of a black hole binary and a star, what that means is that you can very dramatically go from an orbit that's pretty safe with a very large pericenter to a plunging orbit. And you can produce a much higher rate of these events. But the actual flare won't necessarily look that different. Now, if you move the black hole in even closer, so that it's closer to the orbit of the debris stream after disruption, it will change the dynamics of that orbital debris stream, but it could also do things like cut off, it could accrete onto both black holes, it could cut off the flare by pulling out part of the gas that was going to continue to come back to one black hole, but now it's going to the other black hole. So it can really, we see all these smooth light curves like this, and I mean, it's actually quite smooth in the observed bands as well, but it might look choppier or something like that if it was around two black holes.
I think there were a couple more questions in that part of the room, so we'll go back over there.
I like how conceptually you showed the tidal wave of the Earth and the Moon.
Yeah.
And how, especially if our kids have taken prior knowledge and taken it to this level. My question is how we teach energy and binding in orbitals. Can we use that as a conceptual to jump into where we talk about energy in reference to?
I think I missed part of that question. You said your question is, and then I didn't hear that last.
Just like you use tidal waves of Earth and the Moon, you talk about the tidal waves and how it worked, and it really, to me, it worked out really nicely in teaching young kids. In reference to looking at energy and things of that nature with a black hole, what we teach like in chemistry or early physics of energy, energy levels and things of that nature, and how we're moving it back and forth, can we use that as a conceptual to come to this part here, and is there a relationship there?
Are you talking about to understand how the star is disrupted, or how okay. I think probably, I have to think about that more. I think, so when you're thinking of the photon level, energy can definitely be thought of as like discrete levels. In this case, we're talking about like gravitational energy and kinetic energy of gas particles, so it's a little bit, it makes more sense, or it's easier to think about as more continuous. So I generally just use the, tidal, the waves that we see on Earth as a better approximation, but we can talk more, I'm not, yeah.
Hi. So going back to the previous question of this binary black hole, if this tidal wave disruption happens there near a binary black hole, then hypothetically, can we see a change in the characteristics of the gravitational wave?
Yeah, so it probably won't, so there's a couple different anytime that you have two close orbiting bodies, you could get gravitational waves. I mean, me jumping on Earth in principle produces gravitational waves. But for the ones that we'd observe with, for example, LIGO or LISA, right now we're mostly observing black hole binaries. With LISA, we actually think that we'll be able to observe supermassive black hole binaries orbiting inwards, maybe related to your question, or maybe that's why you're asking it. I don't think that putting a star in there is going to dramatically change the sort of signature that we get, because it's a millionth of the mass of the orbiting body, so it's kind of a tiny perturbation. That being said, if you just throw, say, a 10 solar mass object at a supermassive black hole and don't have a second black hole, then we certainly will be able to watch that in spiral and see the effect on the and measure those gravitational waves. We call those extreme mass ratio in spiral events. Pretty self-explanatory. We think they'll probably be most useful from small black holes falling into big black holes, and the reason for that is the same as the neutron star argument. Is just that the black hole can get a lot closer in. It's not going to get disrupted, but it will fall within the event horizon, eventually merge. But because of that, there will be much stronger perturbations to the gravitational field, but you could potentially get it with like neutron stars or something as well.
You had a question in the back there?
I was wondering if you could explain a little more about that binding force equation. I don't quite understand where that's from or what it means. I would think of a binding energy, but
yeah. So if you the way that I generally think about this is if you substitute the second mass of the star with like a little piece of gas from the star, the amount, how bound it is to the black, I guess this is a force, but if you did it in energy space and just removed one of the radius of the star values, how bound it was to the black hole or to the star would be gm star over r squared if we're doing force, or r if we're doing energy. And so if you just integrate that, if you do the integral from the center of the star outwards and think about the gravitational force between the layers of the star, you end up getting something that's of order gm star squared over r star squared, which you could also think about like two halves of the star, how much force they have on each other, and get a pretty similar relation. So if you're doing it more precisely, you get factors of 2 or 3, but we are ignoring those because we're astronomers.
Yeah, we can go in the back, and then we can also get a microphone up to the front of the room here for the next question.
Thinking about the eccentricities of those orbits, eccentricity being greater than 0.99, and looking at what stars are getting eaten by these black holes, like on cosmological timescales, these stars are they forming within this orbit, or are they falling into that orbit, or is the black hole forming while the star was in this orbit? Or
yeah, that's a really good question. We're trying to, this talk, the one thing that I was showing that we could potentially extract from modeling already is the mass of the black hole. We'd love to actually also extract properties of the stars, because outside of our own galaxy, it's very, very hard to look at stars on these small size scales, which is also why we can't measure their orbits close to the black hole. But we think the properties of stars in these very, very dense regions might be different from the properties of the stars out further close to us, or in the outskirts of galaxies where they're easier to observe. As for where they're born, they're probably born mostly you can have mergers of stars, and you can bring more stars in with time. Most of them are probably born pretty close to the black hole, but by close, this could still be like parsec level scales, whereas it would still be many orders of magnitude larger than the radius at which they get disrupted. But this also depends on the type of star, right? More massive stars are going to die quicker. And so if we see a more massive star disrupted, it probably has to form close by. But if you see a very small mass star or a stellar remnant like a white dwarf disrupted, if you can constrain that, then that could have come from further away, because it would have potentially had time to interact dynamically with other stars, or maybe you have like a merged dwarf galaxy or globular cluster that comes in. Yeah, so it depends a bit on the type of star.
I think they're okay. Yeah, we'll go there, and then there were some questions in the front also.
On your slides for the stream collisions.
Yes. I think it's after this. Let's see. Yes.
So I'm understanding that's the star coming into its orbit and then the pieces on the other side.
Ooh, good point. I should have clarified. So this is all happening after the star is fully disrupted.
Okay.
So we actually could potentially, there's been theorized that you could maybe get an X-ray flare from the initial shock of the star getting compressed and torn apart. But most of the energy is coming back from that accretion process, which Eric, what you explained very nicely, is incredibly efficient. And so that's at later times.
Okay. All right. And then I know your graphs were doing this all over a matter of days. But what is the time frame for something like that to happen?
Yeah, so the orbital period at the point of stream collisions could be hours. It's at much smaller radii than and so that's actually really important for trying to understand what sets the evolution of these light curves, because all of this messy stuff is happening at small radius. What effect does that have on the light curves? Well, if it's happening on timescales that are shorter than this mass return rate at t to the minus 5/3, scaled by a week or a month or something, then the effects will mostly probably get smeared out. And so it will be harder to see their effect on the time dependence, just because they're happening more quickly.
Okay, thank you.
All right, now we'll go back over there while we're running the other microphone up front to this side.
I was curious how you would know which way to focus your telescope into space. And then if you detect a tidal event, you have to make some quick calculations to track the star and focus your telescope?
Yeah, so I am not an observer, but so other people will be able to answer this better. But in general, for tidal disruption events, it's nice because you can point at the centers of galaxies. If it's generally looking for supernova or other transients, that you might point into the parts of galaxies where you think these would potentially happen. But it's absolutely true that you don't know what's going to happen. So what observers are doing is just looking periodically all over the sky for these events, specifically at the centers of galaxies, and seeing if they see a flare of light that wasn't there in the last observation.
Yeah, we'll talk about this a lot more in the afternoon, but the short answer is basically you have to look at a bunch of galaxies.
Yeah.
So if it happens once every 100,000 years in our galaxy, you need to look at like 100,000 galaxies like ours to find one every year. And so we can do that now. It's pretty cool.
Yeah. There's a big motivation for the Rubin Observatory that's coming online, is to image the entire sky very regularly to look for these sorts of things.
Can I ask, how many black holes do we have in our?
Oh, I should know this. Actually, I'm not sure. So, okay. Twiddle 1 supermassive black hole. It's possible there's other massive black holes in the galaxy that we haven't seen, but there's some theories for that. But mostly going to be stellar mass black holes. I actually don't have a good number of that. Does someone else have that on the top of their head?
Ooh, that is a good question. How many smaller black holes in our galaxy? We've seen like a couple hundred of them with gravitational wave signals now, but those are only the those are pretty nearby ones that we can. Most of those are in other galaxies, actually, yeah. But then, because we only see those when they're merging. In our galaxy, you can see stellar mass black holes by looking for bright X-rays, and you see those when they're in binary systems with other stars. Because so they'll like pull gas off their companion star, and that's how you get the gas that heats up and produces light we see in those. So we know about hundreds of those, but Adele might know better than me, not to put you on the spot. 80? Okay, cool. 100, 80, same difference for astronomers.
Theoretically, so those are observed ones, so I want to clarify. Theoretically, we would expect many, many more.
Yeah.
It's only the massive stars that are going to die and become stellar mass black holes. And the birth mass function of stars is very, very strongly peaked at low masses, below actually the mass of our sun. And you'd need to be above the mass of our sun to be exploding and becoming a black hole. So really, theoretically, what I would do is just look at that mass function, integrate under the curve at the larger masses, and use that to estimate the total number of black holes. But it would be, what's the number, the fraction of stars above 5 solar masses is also a number I don't have off the top of my head.
It's really small though, yeah.
Yeah.
But there's still so many stars in the galaxy,
But-
it would be a large number of black holes
Yeah,
in the end.
Yeah, definitely.
But yeah, then you need
I'll
gas
get back
next
to you
to
on
them.
that. I can do that.
Yeah, we'll give you a number after lunch. But yeah, then you need ones that you have gas next to that you can see. So then it turns out there's only about 80 that we can like directly observe in the Milky Way by looking at them accreting this gas. But there's probably lots and lots more. Great questions.
If you look at the flare,
Oh, yeah.
and you look at the spectroscopy, can you see the different elements as they're coming off?
I should have included an actual spectrum in here. You can actually, which is really, really cool. I'll just go to the SED. So this isn't a spectrum, right? These are binned energy bins. But if we actually looked at, if we divided, it's like a very coarse spectrum, I guess. If you divide this much more finely, then you can actually see peaks from different elements. It turns out that these events don't, probably because the gas is so hot, the electrons are highly ionized. They don't show as many lines as a lot of other events. But we do see hydrogen and helium lines very regularly. The width of those lines is related to the velocity of the gas, which is really cool. We also are seeing things like nitrogen and carbon lines. I'm very interested in that personally for trying to constrain the masses of the disrupted stars, because the amount of these slightly heavier elements for astronomers, more than hydrogen and helium, will tell us something about the age of the star, which is really cool, and its mass.
I had a question about telescopes, but it sounds like we're going to learn more about that later.
I'll defer for those, yeah.
Excellent. Yeah, I think we had a question over here. We'll go over there and then back over here.
So when you talked about so all these events that are happening, and in the last talk we heard about, we were talking about like time dilation and all that thing. Does that affect, or do you have
the time dilation?
Take into account when you're looking at all this light coming in and you're doing all your calculations?
Yeah.
How does that affect everything?
So time dilation from the black hole's gravity is really only going to become noticeable very, very close to the event horizon. So if we're measuring so sometimes you can see this in X-ray spectra, where we actually do see the disk forming. We're able to, in this picture I showed, somewhere in here. Yes, in this cute little picture here, if we're actually looking, for example, down this sort of funnel, so I assumed it was a spherical cow analogy. In principle, there's actually there's viewing angles in where you might be able to see more disk emission. If you get those and you're able to look much more closely, you get X-ray detections and you can do some of those measurements. What's really actually probably more noticeable time dilation is from the expansion of the universe. So a lot of these you have to redshift correct the light curves, which is an effect on the wavelengths that you see, but it's also changes the time slightly. That's probably the more noticeable time shift in these.
This is for both of you. How did you guys get interested in this topic, and do you have any pearls of wisdom we can pass on to our students?
Ooh, that's a great question. I love that question. Yeah, I guess for me, it's kind of the stereotypical story in that when I was a kid, my dad was really into amateur astronomy. And so we'd go out to, parks and set up a telescope and do camping. And at some point I started asking lots of questions about what we were actually looking at. And then I was also fortunate because my mom actually studied physics in college. So she, encouraged me to ask these questions and started answering some of them. So it's sort of only natural by the time I got to college that I knew I was interested in astronomy. And I kind of happened into TDEs a little bit by accident. I was, in my second year of graduate school, and I was looking around for a thesis project. So I was basically going and talking to different professors and finding out who had a cool project. And the professor who ended up being my thesis advisor said that they had these new observations of a black hole eating a star. And I basically went, that sounds really cool. And so then I, still think that's really cool. And I've continued working on that ever since. But in terms of advice for students, I think get a really good physics background. Some people who are interested in astronomy don't realize it's astrophysics, so you really do need to know the physics and the math. And these days, I think getting some programming classes and some, knowledge of Python in particular, a lot of astronomers use. But programming and statistics is also really important. As we find many more events, being able to do statistics on these large data sets is a really useful skill. And that's also a very broadly applicable skill. So even if you get further along in your education and realize that astronomy is not for you because black holes are boring, you're probably going to still find those programming and statistics skills to be really useful. But I'll let Brenna answer that question too, because I think it's a great question.
Yeah, funny story. We actually grew up in the same hometown, but didn't realize that until much later. But I actually didn't. I mean, I thought that I have a distinct memory as a kid of having a really great science teacher, like you guys, who talked a bit about black holes with us. And I remember just asking questions and thinking it was the coolest thing. But then when I went off to college, I was thinking I would probably try to do maybe some sort of environmental science or environmental engineering, which would also have been super cool. But I ended up studying physics just because I really loved math and wanted to understand the way things worked. And so actually, before that cool science teacher, I actually didn't really like science that much. I liked math and reading. So then, yeah, so I wanted to understand how things work, and I actually slowly found my way back to astronomy. I started doing other types of physics research first. One of the things that I really love about it is how it combines a lot of different aspects of physics. It combines general relativity with thermodynamics, with, I showed how you can do a lot with just manipulating simple Kepler's equations and Newtonian dynamics, which is really, really cool. And this kind of synthesis was something I was really excited about. But yeah, definitely did not come from much. My parents are not scientists. But I guess advice to students, certainly having a strong physics background is really helpful. But I think more generally, if you're thinking about doing research science in particular, is to think about, I guess, like the way that you like to work as much as the problems that you like to solve as well. Research science is you're getting very deep into these very specific questions. It's nice to do things like this and kind of broaden it back up actually. And it can be, and so yeah, thinking a little bit about the way that you like to work, I think is also important, and is very, you could apply these same skills of math and physics and computer science to a lot of different types of scenarios, but the actual day-to-day experience might be pretty different.
I think that's actually a great question to wrap up the morning on. So I'd like everybody to thank all of our speakers again. And we're now going to pause for the lunch break. We'll be back here at 1:30, and lunch will be in the courtyard where you just had your coffee. And we will distribute the scientists among the lunch tables, so you'll have plenty of chance to keep talking to us and ask us a bunch more questions. See you over there.